Introduction. So today the goal is actually to show people that there are still vulnerabilities in InfiniBand architecture, and that actually applications that are trying to make use of RDMA networking, they should actually pay attention to this and also take action soon to address the vulnerabilities. So you probably know that RDMA is actually extremely popular. We have more and more systems every year. Actually, I made this slide 1 year ago, and then I definitely could extend like 10 more systems, but I think it's enough to see that RDMA is actually used, and then it's used in productions, used in Azure cloud, and is also offered in other different clouds. But here, I first like to focus on like what is the difference between like this traditional socket-based networking and RDMA. So in traditional socket-based networking, when we get the packet from the network, what network controller does is just DMA's packet to the driver, which resides in the kernel space. And then if this connections was from the user space, the socket connection, then the driver would copy this to the user application. And if this connection was also, it could be created from the kernel module, then actually it would be copied. The content of the TCP packet would of the message would be copied to the kernel module receive buffer. In case of RDMA, so we have RDMA capable NIC, and the connections, they do not rated in the driver, they not exist in the kind of kernel space, they fully exist in the RNIC. So the RDMA capable device is fully capable processing the packets and actually copying the content, the payloads, to the memory of the user space application, as well as in the kernel space. Actually, you have special API, which is like extremely similar to IV verbs, that allows you to work with RDMA from the kernel space. So, and the overall, what I actually aim to show today, that if we have this setting, when we have RNIC, we have user application, kernel module, working with RDMA, and then if we have an attacker, so which is from the user space, then actually it's capable without any administrative permissions, just from the user space, impersonate user, like any connection to the user application. So it actually sends messages on behalf of the user application. What is more, it can also send messages on the behalf of the kernel modules that use RDMA. So basically, any RDMA local connection can be impersonated from the user space. And finally, that is when I always say InfiniBand architecture, probably know that it's actually not only including InfiniBand protocol, it also includes RockKey-V1, RockKey-V2, so it's like family of protocols. So that's vulnerability that I will discuss today is actually covers all that protocols. But first, I think I'd like to also mention what is the implications. So if we can actually manipulate any local connection again, then we could manipulate connections from the kernel modules. So if we can manipulate connection in kernel modules, then we can actually bypass the security mechanisms that exist in our operating system as we send something on behalf of the kernel. And one of these examples that I would like to focus today is actually NVMe-oF fabric. So this is a kernel module that is running in the kernel space and which allows you to have this block access to the remote device. So right now, I'd like briefly explain what NVMe-oF fabric protocol is and how it compromises security by using RDMA. So overall, NVMe is actually just a protocol which allows CPU work with NVMe devices through PCI Express. So the idea was that it's also works zero copy, lower overhead. Everything is performed by the DMA engines. It's actually quite similar with the idea of the RDMA. And that exists because like it works on the notion that you have this SSD that has a special controller which would process this request. Yes, so that is what is happening. So the biggest problem, like what you could face if you just work with NVMe, you have a limited number of slots in your PCIe bus. So you would be limited just by 3, 4, 5 disks. But what if you'd like to go to some large scale? Then there was the idea of to extend this protocol and actually work over the network. And actually, when you work with this NVMe, as you work, it's actually protocol on top of PCI Express. It was offering speeds of PCI Express as well as latencies of PCI Express, which was extremely low. And then you have like probably extra latency on the controller and on the storage media. But it was actually on the level of it's on the level of like 2 microseconds. Of course, on the idea of going to the network, you want to, then you could be able to attach this remote NVMe, which are on the remote machine, and then you could forward this request through the network. And of course, if you would like to stay at this level of like microsecond latency, you want to use something fast and zero copy. And here, the idea was that you could use actual RDMA. And if you use RDMA, you could actually take a lot of disks. You could actually enable this so-called disaggregation, storage disaggregation, when you have like local operating system attaching like multiple storage devices, and the application, they would even notice this. So if you were 2 microseconds, it became like 4 microseconds. It's still not noticeable by the most applications. And local access, it seems like the remote. And you could have like almost infinite, like really large number of remote disks. So in the sense, what the model, like thread model that I would like to cover today is, imagine that we have 2 machines, remote node, which has SSD attached. This is the machine which runs NVMe target application in the user space. And we have a local node, which has NVMe client application, which mounts this remote disk. And then on the same machine as a client, the client operating system, we have this user that is malicious. And the goal is actually to show what, like when you actually work with NVMe, of course, the idea was that when you have this kernel module of NVMe-oF fabrics, it's called NVMe-oF fabrics client, then most likely your application, it's not even planning to work with the block access because you need sudo permission. So the idea that you would install some kind of file system on top of this. And when any user would actually try to work with the disk, it would work with the file system. File system would actually check the permissions, then file like that. Then these accesses would be mapped to the NVMe commands, and then these commands would be sent over IB verbs to the remote machine and executed. And this is basically the setting that we have. And actually, what I will show you in a few slides, that the user basically can bypass these checks. It bypasses the file system and NVMe kernel because it can directly manipulate IB verbs. So it could go directly to the IB verbs user space driver and kind of send the packets on behalf of any other connection. And to show it as an example, I would like to show you what actually means to send this NVMe command. So in the simple case, if you'd like to write, for example, block of like 512 bytes to remote NVMe, the applications, again, build a NVMe request and just send it with RDMA send. Then it would be received by the remote machine. It would write it to the disk. It would get the completion event, and then it would send the response back to the client. So this is like really basic request, which allows you to write anything to the block. So what is actually happening? So this is like example how RDMA packet look like. So we have the routing, we have transport header, and then we have a payload. And this is payload that's actually just encapsulates NVMe write capsule. So it would have such information as like block address, data that it should write. So it's actually just basic information required to perform write request. And how this packet is actually processed. So it first gets processed by the RDMA NIC. So this RDMA part, so the rest is this transport header routing checksum. They disappear after they pass the NIC. And then after they go through PCI Express bus, the only payload would be in the receive buffer. And the application, this transfer target kernel module would execute this request. The biggest issue with that kind of model, like what's happening, that there is no security here. So in these capsules, there is no field to actually authenticate sender or actually to verify who was the sender. There is no check like message authentication codes. There is no identity check. So once the data hit the receive buffers, it will be executed. So there is like no checks almost at all, just sanity checks to check that the capsule is built correctly, but there is no security involved. What it actually means that the whole authentication of the request at the destination happens on the NIC, and it actually happens on just matching the connection ID. So if you could forge a packet on behalf of any other like on behalf of a connection, other connection, then you could actually just send this request right into the memory, and then it would be executed. So right now, I would like to show how we could actually forge a packet with QPN that we actually need. Basically, how we could build a packet on behalf of somebody else, or like impersonate somebody else. And that actually comes, like why we can do that. It comes from two major vulnerabilities in this InfiniBand architecture. So the first, if you like work with RDMA, you probably know that you work with IPverbs library. In the IPverbs library, the model is like, yeah, you don't have any special permissions. You use from user space, and then you just create connection on your local RNIC from the user space. And how it works that the device would create any connection you want. So it will not even ask anything. So you just, as a user, you would just send the request through IPverbs, create a QPair connection. So this is endpoint of a RDMA connection. And the device would just create it and just say, oh yeah, you got connection with ID 100. And then what you do next, once you get this connection, which is unconnected so far, you would just provide it a bunch of information and about the receiver, and then you would say like routing information, remote connections. Oh yeah, please make this local connection to send to that given endpoint X. And the device will do it. It will not even ask you, okay, whether it's exists this QPN, whether PSN was correct. It would just create it. And you could just try. I mean, it may fail. So this connection may fail, but it may work. And then this packet would be sent and received. So, but important part that there is no sanity checks. There is like nothing device does special when the user tries to create a connection. And the second vulnerability, which is like most serious and the core vulnerability, is in the packet format. So if you look how the endpoints understand who was the sender, it's actually understand it from the QPair number. The packet contains only information about the destination, and it does not have any information about the source. So the idea is clear. It's point-to-point connection. Why would you need to have information about the sender and the receiver? If it's like, if you know the receiver, you know the sender. If you know the sender, you know the receiver. And probably when the InfiniBand architecture was designed, the idea was, okay, let's remove one. So it's enough to have destination because it actually helps. So you have destination, the receiving NIC checks whether it has this connection, and then it's processed. So this is clear. But I will show you on the next slide why it introduces huge security problems that the packet has only information about the destination connection ID and has no information about the sender, what connection ID actually created this particular packet. So let's imagine the case that we have remote machine. It runs Rocky V2 protocol. It has IP address for routing 1, 2, and it has a connection endpoint with ID AB. And we have a client that resides at address 1.1. And then it's, for example, this could be user, it could be kernel module, and then it wants to establish a connection to send to this endpoint. What it will do, it will, again, ask the device to create a connection. It will get, for example, connection 100. Then the application sends, okay, I'd like to send this through this connection to remote connection AB, which resides at the host at address 1 point. Okay, the device will work, and then you can actually start communication. That would be perfect. But actually, at the same time, if we have another user, it can also create any connection. So everybody has a permission to create a connection. So the adversary would create a connection, would get completely different connection ID. Of course, it should be unique and at the local node. So it would get, for example, 1 to 3. But actually, the attacker could add the information about the same endpoint that actually can say, oh, I'd like also to send to connection AB at the address 1, 2. And it will work. So, I mean, you could check today after the presentation. And what is interesting, if we send a packet or like a message from both this connection, what comes out of the port of this local NIC, it looks exactly the same. So there would be the same routing header, that would be the same transport header, and then you're free to choose any payload you want. CRCs would be calculated by your RNIC, and basically, once it's in the network, you cannot even understand who made this packet. It could came from the attacker, it came from the legitimate user, and like, yes, of course, you could ask, okay, what do we need? Actually, we need some information. So for that, you actually need to know the connection ID. Actually, I described in the paper that it's predictable. And for NVMe application, this is extremely predictable because usually NVMe kernel modules, they're loaded at the boot. And all the RDMA devices that at least I have access to, it's like more than 20, like 3 different vendors, 20 different devices. They all have initial connection ID, which is something around 100, 200. So it's actually like enumeration space is quite small. And then if you know the machine, you always know what is the like this first QPN after the reboot. So it's not hard to predict. And then about the PSN, so it's just small packet counter. It's 24 bits. You can just enumerate it. So enumeration of 24 bits. I don't remember exactly the number, but you can do it definitely within a few seconds. So overall, this attacker could just have like simple enumeration, and within like few seconds, it could just made a NVMe write request and then change the content on the remote machine. So it can actually change what is stored on the disk. And then it can change any block. So it could just say, oh, I'd like modify the block 1000 and write whatever it wants. And then if you can actually change anything you want on the block device, then you could actually change the whole behavior of your operating system, which we found extremely dangerous. And what is funny, I did the same experiment when I established also IPsec over Rocky protocol, and then I could do exactly the same. And the reason is the same. Basically, IPsec is the protocol which offers you protection at the IP level. So IP level protocol has no idea about RDMA connections, that there is QPNs, and the packets also look the same because IPsec is designed to protect packets from port to port, so from IP to IP, and it has zero information what is happening after the IP level. So that's exactly works if you even have IPsec over Rocket deployed. Of course, this extends not only to this NVMe write request that I just described. The protocol also has this NVMe write general, which are like for sending large messages. Of course, you cannot just send like to provide buffers for using simple RDMA sends. There are like, if you would like to send something longer, you need to use RDMA reads to fetch the data, or for the reads, NVMe fabrics reads, they use writes. Actually, in the paper, which was linked and mentioned in the slides, you could see how we could use this like forging tool, the ability to create RDMA packets, actually to affect the work of NVMe Fabrics protocol. So you could like have really interesting attacks. Overall, what I was talking to, it's not just I made a forging tool and check that it works. Actually, it was tested, and I made a tool and like I tested the attacks for SPDK and also for Linux kernel modules. They have different behavior, different implementations, and all these side effects I describe in the paper. But the difference between them, that SPDK is actually was designed to work from the user space, so actually to allow applications like databases to take advantage of NVMe storage media without going through the kernel. And the Linux kernel module was designed to offer block device to the Linux, so you could actually use the rest of the infrastructure and work with NVMe and the NVMe Fabrics disks. You may wonder right now, okay, I tested, I showed that it's possible for SPDK for Linux kernel, but probably in this NVMe Fabrics protocol, there was some security introduced. Actually, they released new standard just a few months ago at the end of last year. Yes, actually, they introduced this two mechanisms. So the first one is called in-band security. And actually, this in-band security is designed to just authenticate connection at the connection establishment. So you just can challenge the client or the target, or like they could challenge each other, check whether it's the disk it wants to connect and whether this client is allowed to connect. But our attack shows that actually you can reuse any existing connection. So you don't need to create a connection with target or the client. You can just send messages on behalf of the created connections. And also there is suggestion to use IPsec for RDMA, but as I showed, there are like cases when IPsec does not work. So overall, if we would talk about this TLU model that I introduced, this various spoofing of request responses or corrupting memory with RDMA writes, this is all possible. But I have in the other model, which I described in the paper, what if we have this attacker on the remote machine? Of course, IPsec would prevent it. So we cannot bypass IPsec security if we just see it at another end host. But the rest is possible for this in-band because it doesn't provide any actual security against injection packets into existing connections. Overall, actually, this paper was only about NVMe. So I actually also did some analysis of connection manager, found interesting vulnerabilities. Also on the congestion control. I think if you're interested in security of RDMA, I would suggest you to just skim the paper. It's on archive. It's not actually submitted anywhere so far. Feel free to read it. So, and overall, what is the mitigation? So the general mitigation is like from easiest to the more complex solution. First is change the packet format and add the source QPN. Then you could actually avoid this injection, because then you could actually distinguish packets sent by two local connections. Another option is actually to inform application that they should do something from the application layer. And actually, it's possible for NVMe. NVMe uses RDMA in quite simple way. It's just let's say sending the data and sending the data to disk. So it's really simple. And then you could actually have application layer authentication for this protocol. Even if it's not possible in general, it's possible to do for the NVMe Fabrics protocol that I expect that should be extended to the standard. Another like possibility, if we say that we change the packet format, the community can make an effort of having secure transport. If you need to change the standard, you could also introduce secure transport. And finally, there was actually a proposal which would also presented at Usenet Security. There was the idea of having additional infrastructure to verify the packets. And actually, in this work, they also mentioned they use these tools that actually can help to catch these forged packets as we propose in this work. It's, I think, also interesting to read. This is not written by us, but I think it's really nice read. So overall, on that, I would like to conclude the talk. So, and I'm happy to answer your questions.
Thank you, Konstantin. I actually read the paper. I thought it was a very well-written paper, so congratulations on that. Do we have any questions? I don't have anything queued up. I've read the paper a couple times, and I thought it was a great paper, and I have no questions. Does anyone else have any questions? Okay. Well, I do encourage people to read the paper. It is a very good paper. Okay, thank you very much.